and welcome to the second part of Unit 3. In this part, we're going to deal with examples of one-dimensional kinematics. To begin with, I have a list of steps to take when trying to solve these problems. Step 1 is draw a picture. The picture organizes all of your thoughts. It helps you understand what is being written in the question and what is being asked for. In your picture, make sure you define your coordinate system. Locate where position equals 0 in all necessary directions. In one dimension, there's only one, but shortly we're going to get to two-dimensional projectile motion, and then you need a 0 in both directions. Indicate the directions of the initial velocity and the acceleration with arrows. Write your grocery list. Grocery list, what is it? It's a list of the variables that you know, that you don't know, and what you want to know. Okay? It's like when you go shopping, you have to look at the recipe, figure out what the ingredients are, what you have, what you don't have, what you need to buy. That's why I call it a grocery list. Okay, look at the equations and figure out a way to solve the equations simultaneously to give you the answer that you are looking for. You may need to solve for an intermediate variable before you can find an answer. And make use of things that you know. For example, velocity goes to 0 momentarily at the top. Symmetry. If you go up and down to the same height, time up will equal time down. If you look at the velocity, if you go again up and down to the same height, the initial velocity you had upward will be your final velocity going downward. Make use of symmetry when you can. The first example involves a car. It is slowing down uniformly from a speed of 21 meters per second to rest in 6 seconds, and you want to know how far it traveled. This word uniformly is key here because that's the thing that tells you that you have a constant acceleration. Okay, so following the method outlined, you have a car, and some time later you have the same car. Here it is moving this way. It's our initial velocity, and it equals 21 meters per second. I'm going to let this position equal 0 because it's my coordinate system and I can choose the 0 wherever I want it. It's also where time equals 0. Over here is the position x that I want to know, and I'm told in the problem that this occurs at 6 seconds. I'm also told in the problem that it comes to rest, which means it's not moving. And because it is slowing down, the acceleration has to point opposite the direction of the initial velocity. Before I finish my picture, I want to make sure that I put down my positive direction for my coordinate system. So in this case, positive x is going to be to the right. I can now move on to writing my grocery list. The grocery list includes all the possible variables that I have in the problem. So I have x, the position, x naught, the initial position, v, the velocity, v naught, the initial velocity, the acceleration a, and time t. And now I can look at what I have up above and interpret into my grocery list. I see that at time t equals 0, I've defined my position as 0 and my velocity at 21 meters per second. So I put those in for all of the initial information that I want. I see that at a time of 6 seconds, I have a velocity equal to 0. So I can put that in, that at time t, my velocity equals 0. And I also see, hey, look, this question was asking for how far. I have a question mark there, so I'm going to carry my question mark down here. And now I'm going to think about my constant acceleration equations where I've simplified down to one dimension and dropped some of the subscripts. Okay. I want to know x. I see I have two equations that involve x, the top one and the bottom one. However, both of them also involve the acceleration, which I do not know. Therefore, in order to solve this problem, the first thing I need to do is find the acceleration. And the easiest way to do that is going to be using the middle equation. So v equals v naught plus at. So our velocity at time t was 0. Our initial velocity was 21 meters per second plus our acceleration, and then took 6 seconds for the car to slow down. Solving for the acceleration gives negative 3.5 meters per second squared. And I say, ooh, it's negative. And then I look at my picture and I say, I defined positive to the right. My acceleration is to the left because this car is slowing down. Therefore, it should be negative. So that's okay. I can now use either the top equation or the bottom equation to find the position, x. It is easier to use the top one because that does not require any algebra to solve for it. Therefore, I am using it. I can now plug in my numbers. 21? 21, yes. 6 seconds plus 1/2 times negative 3.5 meters per second squared times 6 seconds squared. If you put all that into your calculator, you find that it took 63 meters for this car to come to a stop. The next example involves a baseball hit straight up. Oh, there's a slide before that. Hold on. The next example does have a baseball getting hit straight up. And for that, we need to know the acceleration due to gravity. The acceleration due to gravity always points downward and has a value of 9.8 meters per second squared near the surface of the Earth. Okay. So you're like, okay, well, how close to the surface of the Earth do I have to be? You could be on top of Mount Everest. It will not have changed that much. So over the normal path of a ball, using a constant value of 9.8 meters per second squared is acceptable. Okay. Notice that it has a value here. There's no sign associated with this because this is a magnitude. This magnitude is known as the acceleration due to gravity and is given the variable g. And here is our baseball example. Baseball is hit nearly straight up into the air with a speed of 22 meters per second. Lots of things we want to know. How high does it go? How long is it in the air? What's the velocity at the top? And what is the velocity when it returns to its original height? Okay. Following the procedure outlined a couple of slides ago, draw a picture. So here I have my baseball being thrown upward, 22 meters per second. It's going to be under the influence of gravity, so my acceleration will be g. I'm free to put my 0 anywhere. We typically use the vertical axis as 0, so I'm going to go with y instead of x for my variable here. I think I just misspoke. We typically use the vertical axis as y, so I'm going to use y instead of x here, and I'm going to let 0 be at the bottom of the motion. I'm going to look at a couple of points. The first question is, how high does it go? So that is up here. So this is a question mark. How long is it in the air? That is also an unknown. What is the velocity at the top? And what is the velocity when it returns to its original height? The last two questions we can answer without doing any math. At the top of the motion, the ball has to stop. So v will equal 0 meters per second at the top. It stops only momentarily, but it does stop. What is the velocity when it returns to the original height? When it returns to the original height, since we have symmetry in this question, it will be moving downward at 22 meters per second. So the velocity when it returns to the original height will be 22 meters per second downward. Okay. You can actually do the math to show that latter one fairly easily. I now need to write my grocery list out. Our initial height we defined as 0. Final height is one of the things we want to know. We know velocity goes to 0 at the top. V naught is going to equal 22 meters per second, and it is, assuming we let up be positive, it'll be a positive 22 meters per second. But since gravity is downward in this coordinate system, our acceleration has to be a negative 9.8 meters per second squared. And time is the other thing we want to know. I can now think of my equations. Here they are. I want to know time, and I want to know y. I could find the value of how high right now by using this equation right here. I also could use this equation right here to find time. Either approach will work. However, since I need to find time anyway, I'd rather use this equation to find time and then plug into this equation to get the answer to how high. So V equals V naught plus AT. Final velocity at the top was 0. Initial velocity was 22 meters per second. Our acceleration is negative 9.8 meters per second squared times time. Solving for time, you get 2.24 seconds. I'm going to make a little note here that this is to the top. The question was a little bit vague. It said, how long is it in the air? And so that is the question of how long does it take to get to the top, or how long does it take to go up and come back down to the original height? If I want the time for up and down, then I'm going to call that the total time of flight, and it will be double that number. So 2.24 becomes 4.48 seconds. Remember, this is up and down, returning to the original height. Now I have definitely answered that question. Finding how far up it went, I'm now going to use the first equation. Initial position was 0. Initial velocity was 22 meters per second. Our time to the top is 2.24 seconds. That was a second that didn't work out very well. Times 2.24 seconds squared. Putting that into the calculator finds that the ball travels upward 24.69 meters. I have now answered all the parts of that question. One final example for this section again involves a ball thrown upward. We're told how fast it moves when it's thrown, and we want to know how long does it take to reach a height of 10 meters. Okay, so again, drawing my picture, 20 meters per second is my initial velocity. I'm going to let where it starts equals 0 meters. And that's my t equals 0 point. Come up here. This is at a position of 10 meters. And I don't know how long it took to reach there. The other thing I don't know is I don't know how fast it's moving at this point either. I'm going to again let gravity be downward. And for a change of pace on this one, I'm going to let the positive direction be downward. Okay. I can now define my grocery list. Our final height is 10 meters, initial height of 0 meters, initial velocity of 20 meters per second. It's upward, positive is downward, therefore this has to be negative. Our acceleration is the acceleration due to gravity downward. Downward is positive, so this comes in as a positive 9.8 meters per second squared. Okay. If you think about the equations, the only one that has a chance of us finding this answer in one step is using the y equals y naught equation. Final height is 10 meters. Oop, pause just a second. We need to be careful here because with up positive, or sorry, with down positive, if we go upward, our final position has to be more negative than our initial position. So this has to be a negative 10 meters in the coordinate system. Our initial position is 0. We're going to subtract 20 meters per second and multiply by time. And 1/2 times 9.8 meters per second squared, t squared. I can now rearrange this equation. So it looks like 4.9 meters per second squared, t squared, minus 20 meters per second, t, plus 10 meters equals 0. And you may recall that to solve this, you have to use the quadratic formula. And remember, the quadratic formula says that if you have a formula that takes on this form, then the solution is negative b plus or minus the square root of b squared minus 4ac all over 2a. So in the quadratic formula, I can identify the values of a is 4.9, b is negative 20, and c will be 10. Plugging in results in one of two values. I get t equals 3.5 seconds, and that is the positive root. And I get t equals 0.6 seconds, that is the negative root. We now need to identify which of these answers is correct. And depending on your interpretation of the question, they could both be correct. So what is happening here? Well, we're starting at the bottom. We're moving upward. Here's our 10 meter mark. At 0.6 seconds, we've passed the 10 meter mark, moving upward. And then 3.5 seconds after the initial toss upward, we pass the 10 meter mark coming back down. So technically, both are correct, but I think we can argue that the first time is the best time, so the answer should be 0.6 seconds. This concludes this part of Unit 3.